came in something like 2007, when hafnium oxide was the only way out, and there starts the equivalent scaling, right? And the other equivalent is here in multi-layers on top of each other, because now you use the third dimension and keep the critical dimensions here the same. Yeah, so they may say 4N, oh, is that 4 nanometer? No, it's not 4 nanometer. They sort of smuggle the nanometers this way, eh? But it still is, if you talk about logic and what is capable right now, that's that fork sheet. You know, of course, there was a question mark here. Is it now threatening even ASML's business or so or not? Eh? In the scaling, atomic layer processor really came to rescue, because they were still stuck with this immersion deep UV and so at 193 nanometers or so. I have a slide on that. We heard Maxime talk a little bit about the future. There's also a lot of capabilities here. Eh? Did I mention photonic? Yeah, photonic also. Of course, photonic is our friend in the way of that. Well, the wavelengths are very forgiving. It's hundreds of nanometers. Eh? So if you want to have an optical cavity, optical waveguide, what have you, then those dimensions are pretty forgivable. Anyway, there's more than that, because the #1 trend these days is low power. All the business in the internet, I think most of you will know, is in America, it's 10% energy consumption, 10%. Yeah, in the third world countries it will be less, but it is that's quite some. It is your internet, it is your virtual reality or what have you these days, or the dock centers. Okay. But I would say this is beyond more, and it's also, by the way, beyond my brains very often, because I don't know that much about quantum computing or neuromorphic or memory. But these concepts are concepts sort of trying to mimic how our brains work, because that is a low power intelligence system. Wow. Enough about that, yeah. The only remark left, business. If you make the calculation, just the business when Jack Kilby started or so, and it was picked up very soon, worldwide business, 200 million or so, and now it is 600 billion this year. Huh? Or last year it was going down a bit, but if you make just the exponential logarithm or whatever, it's 13% growth per year, business. So where's Maxime? We seem to be in a good business. All right. And now I'll be talking about this part, and I have to watch my time. But I was talking about deep UV and that sort of thing, and now the need for EUV, which was held up for over 10 years. And this is simply the physical sort of a pitch or gate length. Gate length is in blue, and of course it's a logarithmic scale, so it doesn't seem big steps here, but it is still pretty big steps. And here is an interesting sort of inflection point of several things. Here, gate length were smaller than the radiation of the in the litho step or so, and there were tricks. Going to other lasers, using optical proximity correction, using a droplet underneath this one here, which sort of enlarged the numerical aperture and so, and that enabled this sort of things that you are used to, including the gate all around or almost sheet sort of nanosheet sort of structures, and this is mostly for logic. But the tipping point was here for wavelength. But also, and it's important, for going from single wafer to batch. There was a lot of demand starting already here in the mid-90s to have better control in a smaller sort of reactor than those big batch reactors. Batch reactors are still it's very often used when you really have a not too critical process and you want to make high volume manufacturing. Yeah. And high volume manufacturing means that you have 20,000 wafer starts per month. And then again, equivalent wafers. The wafers may be smaller than 300 millimeter, but equivalent is that is the number that really is counting. Okay, more on that you can find, I think that was 2 years ago at the IMEC Technology Day. Okay, well, here I can go. I think everyone knows this, right? Compatible chemistry for a precursor in combination with a surface and its co-reactant. Chuck, 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 layer by layer. And a layer need not necessarily be just the ideal shoulder to shoulder sort of stacking. It could also be a partial monolayer. But anyway, this is about the way to go. And these are the textbook school examples of alumina, the workhorse in ALD. It may be nice to look at the reverse process, which is peeling off, also in 3D, the outermost layers, and then the next layer, and so forth. It's the same sort of sequence that, thanks to Eric Joseph here from IBM, I got this a couple of years ago. First step is what we call, that's another slide I sort of proudly used. Modification. Let me see whether I can do it now. Oh, yeah, this is the PDF you have. Oh, okay, now I know. Anyway, so it's modification, and then you have this layer of fluorine, for example, on silicon. On top, those, yeah, it's a pity that I don't have the real animation, but then you have, of course, a chlorine with another chlorine, coupling chemically to the silicon, weakening that first bond. Sometimes weakening even the second one, and then we may talk about quasi-ALE, as long as you can make it repetitive, reproducible. Once it's there, you take it off with a purge, then you come in with something energetic, could be a light pulse, could be argon ions, as long as it's energetic enough to knock these weakened silicon atoms bond to the chlorine off, and then you can repeat that. All right, this we have seen. I added a few things here. Oh, okay, yeah, now I know. Like atomic layer printing, or look at the neighbors, additive manufacturing. That's the company there. Yeah, there is atomic layer infiltration in all sorts of porous materials. It's what we do at Twente University in membranes. They also call it vapor phase impregnation or sequential infiltration sequence. I don't even know. But that's it, huh? And I think one takeaway message is, folks, do not think it is just 1, 2, 3 separated worlds. They come together, whether you want it or not. My statement is there's no deposition anyway without etching, parasitic, or the other way around. Yeah. Well, here, state of the art. I think I should sort of almost skip that because the PDFs will be there for the audience or not later on, and otherwise you can sort of email me. But today, interesting is that now Micron and Hynix and Samsung have 232 layers of oxide nitride oxide. Oxide nitride oxide. They laterally carve out, etch out some parts of the nitride. Yeah, so the process should be selective, and then they fill it up with atomic layer sort of functions. Does that help? Yeah. Well, you know, such a process takes 2 hours for the etching of this thing. 2 hours. So you have to make your throughput some way or the other. Yeah. By the way, just a regular 20 or 30 litho step process with hundreds or few thousand other steps in between takes how long, folks? 2 months at least. Yeah, and that is why single wafer every now and then, of course, is easier. If everything is single wafer, you could have it in 2 weeks, and then have faster metrology or feedback, that sort of thing. Huh? Okay, enough about this. I guess Erwin will also talk about that tomorrow, and we saw already something like this. This is about ALD, and that's also my message, and ALE, and that's why I smuggled in this yin-yang. It's 2 of a kind. It's 2 biotopes doing the same sort of things, although with different chemistries and so. Yeah, and I already told you that as long as you take away a constant mono or bilayer thickness, then you may call it quasi, but as long as it works, it is fine. Word on this, yeah, you may know that pulsed processing is coming more and more, not necessarily in an AL process, AL whatever sequence, but also pulsed CVD is there. And we always had continuous processes, old-fashioned CVD or old-fashioned sputtering when you take it off. Yeah, but everything was on. The parameters were all on. Yeah, but there's always variations in your mass flow controllers, what have you, and so forth. So this is already a good step to have it pulsed, because then systems can equilibrate a bit better. Yeah, so that comes in as well. The distinction is that atomic layer processing is what we call surface controlled, here it is, as opposed to flux controlled. That I don't want to say that much. ALD here, ALE there. A lot of comparisons. Hello, process control uniform and 3D compatible. Even if you have, and there's one message, ALE can be split in isotropic and anisotropic processing. But there also you can play around with the conformality over steps. But an important message here is also that you can use it for smoothing layers. Deposit something, then take something out, and so forth, and you will see that the initial roughness will get better. And also the problem of classical etching, larger and smaller openings, which is aspect ratio dependent, disappears. That I may skip in terms of time, because I'm already almost running over. Well, ALD and ALE, you separate the chemical and the physical function. This was the IBM work where they combined it and showed that combined they were doing 10 times better in terms of etch per cycle and that sort of thing, or etch rate. So sometimes it is worthwhile to separate this synergetic sort of action between chemistry and physics. All right? Boom. That I may skip. It's all about reaching a saturation also in etching. Yeah? Langmuir isothermal absorption things. It is maybe nice. Just look at these, only the bottom line. Process windows. We know this for atomic layer etching, deposition. Read this as temperature, also there, or as energy. You shouldn't be too low in temperature, not too high either, because then you're out of business. Same thing with etching. You have to be in an ideal window. And of course, etching comes in with, for example, ion energy and what have you, voltage biasing. And then there's also a window where you may start etching. You may start etching too much, or if you have two materials, you would like to have a selectivity window, which also keeps the chemistry in combination with the physics work together. Erwin, will you show something on reactors tomorrow?
Not really.
Okay, well, take this just as a message, and otherwise read Harm Knoop's his article several years ago. And tomorrow we will hear about spatial processing. Usually one has a shower head coming from CVD again, and that sort of thing. And batch, don't rule out batch, because people are, especially in thermal AL processing, this is still good. With ion assisted, it may be a challenge. Okay, just plasma. Shall I once more? Yeah, this is an example we had ourselves. I'm going to skip it, although not completely everything, because this is, I'm still proud to show this. This is about, this is a real takeaway message. It's about atomic layer etching. We started just with a forest of gallium phosphide nanowires, and on top of that there was 60 nanometers of zinc oxide, just done with thermal ALD, and we know that is pretty step conformal. And then we started with a sequence of ALE steps zinc oxide in combination with acetylacetone and oxygen. Oxygen as a plasma, oxygen just regular. This is the thickness, 60 nanometers we started with. Also there. Nothing happens with this combination of the etchant, acetylacetone vapor, with oxygen as a gas. Nothing happens. Just oxygen plasma as such, nothing happens, but it is this synergy that really comes out with, what was it? I think it was 60 nanometers off. No, what is it? Or anyway, it was 1.3 angstroms per cycle. And that is exactly a monolayer of zinc oxide. So you can do really layer by layer etching. And this is how we showed it, and no damage here. As you can see the fringes in the top sort of image here, fringes of the crystallographic phases. And this is before, this is after, at several lengths. This was 6 or 7 micrometers. But the trick to get to isotropic etching in ALE using a plasma is just use very, very moderate biasing, and then if ion energies in argon are 20 electron volts or less, you have practically no ions, but you do have the radicals. Yeah, so you switch out the mother's little helpers, and then you can etch isotropic. This I thought so it's all about ion energies. A typical ion energy distribution function for regular RF is a sort of bimodal thing, and there's a low energy and a high energy tail. Yeah, there are all sorts of tricks to narrow this down and to increase the selectivity and even make it into a sort of single peak ion energy in a very narrow band, which you can tune depending on what you want to etch off. You can tune the energy, you can tune the gas with which you do it. That energy ion distribution function will shift. And it is Karen Koenig who showed that already quite some time ago. Karen Koenig is with Lam Research, yeah, a great company. Few examples, if I am allowed. ALD or ALE or together sometimes doesn't end up in your product, but it is a great way to continue the scaling of your system. And that has been used for many years. For example, in multiple patterning, as they call it. Imagine, first example, so 3 of them, red stars, will leave no or hardly any traces behind in your SEM cross sections and what have you. The multiple patterning, it is here sort of abbreviated as X. It could be double patterning, quadruple, and even octuple patterning or so. What you do, in fact, is you start with this sort, and this is the #1 application of ALD. You don't see it. You may think, oh, there's no ALD in this product. No, it is. Because suppose you just have a photoresist pattern, and you see the aspect ratio is very mild, 2 or 3 at most. You then deposit what we call the spacer, that's spacer 1 deposit. You etch it anisotropically away. Then you end up with these, what we call mandrels. You can do another, and then you already cut the pitch in half. You do another ALD layer, could be also other chemistry or another material, and repeat this. This is then just in quadruple, but you can even do it more than that. And that is how these pictures were taken from samples, how they did it. This is either IBM or Samsung or so. Another way is in contacting, in self-aligned contacting. Best thing is to look here. If you have, let's say your transistors here at the very bottom or so, and they are silicon nitride cap, the first step is very often just silicon oxide on top of that, and then you start masking. But if your alignment is a bit shaky, it won't come all the way down to the contact areas just here, but they may ruin already your transistor structures here and take away too much of the silicon nitride corner. Wow, that you don't want. Also there, in a very delicate process, it was TEL, who came up with this selective anisotropic etch, so the beginning of ALE, which you will not find either back in your system. Hot is really area selective ALD, yeah. So you put on some seed areas where you really choose your chemistry in such a way that the growth is enhanced either by ALD or whatever you try CVD to pick up, purely chemically selective to just do this what we call bottom up growth or bottom up lithography. Yeah, and is this so important? Yes, because if you start doing it classically and everything shrinks, you may end up, because this is what you want to sort of grow onto, you may end up with all sorts of metal defects or contact error. It's called the edge placement error. I'm almost done. Now, this is what we did with Alfredo Mameli part. No, this was at TNO. So imagine just silicon oxide growth. So that is a silicon precursor and oxide, oxygen. But now a third step comes in. So it becomes ABC, ABC. You block with what we call a small molecular inhibitor. Yeah, and here it was ethyl butyric acid. So no acetone, acetyl acetone, but a derivative of that. Very good in blocking your non-growth areas and just permitting that growth here. Of course, there is always something here that might disturb, but then etching comes. You could take that out in an intermittent step. If you do it only, if you let it go, the system go, then the delay is 40 cycles, which is then 4 nanometers. So unpunished, you can grow 4 nanometers here, not there. But if you want to go on, you have that trick of taking away this residue. Wait. Oh, we did that as follows. Right? Oh, it's already. Oh, yeah, it's the PDF. Yeah, sorry. So you etch, and then sooner or later, after 40 cycles, it's too much. Well, then you take it away with. In fact, we took it away with an intermittent CF4 oxygen back etch. Yeah, and then go on, back etch, keep it clean, restore that. And so forth, and that we did in spatial ALD. Yeah, also is a good promise for ATLANT 3D to do something like that. And because at TNO we came with a sort of multiple injector nozzle, and we did indeed patent it and publish about it. But if you in that nozzle also have a section for etching, then you have an integrated ALD ALE machine. That's also one of the takeaways. You will see it merging. I like the word that Maxime used, atomic layer convergence. But the C is already sold out for atomic layer cleaning. Last thing, if we are, and we have entered the 3D sort of world, how do you keep on implanting? I didn't talk about implanting. Yeah, ion implanting. Also an invention of William Shockley, by the way. Again. He had the inventions on the through silicon vials in 57 and in 58 on ion implantation. He was an impossible man, but he was brilliant. And there's more of those examples. Example here, back to materials, is how do we dope a 3D picture like this? This is from Ray Duffy, former Philips colleague, now working at in Ireland at Tyndall Institute. How do you do it? Well, in fact, we call it plasma doping or what is called monolayer doping. So you use ALD but it will not show up in your pictures as a functional layer or so. This was already done by quite a few names that ALD persons may know. Jeff Elam, Anil Mane, Microcurrent, and Tom Seidel comes from implantation. You sort of deposit a layer of alumina which contains also your dopant, boron, phosphor. It sits down as an oxide. You anneal it so that the boron or phosphor comes out, and you take away the residual oxide. Very nice. Okay, we're almost there. Yeah. This is just a selection. Most of the things were on ALE or some on selectivity, but also good review work on ALD, and I started here in 2010. Yeah, you will find a lot of names there, and even recently we had something here on titanium and silicon oxide selective area growth, just accepted. But important also could be this thing here. Thorsten Lill, you may know him. Well, the number 1 or 2 ALE expert in the world, together with Richard Gutschall. He has this book on atomic layer processing, mainly on etching, but also something on deposition. And something I did not talk about is the chemistry. But in the panel discussion, we will do something. The development of specific chemicals, not stolen from CVD, where temperatures are too high, but specific for atomic layer low temperature processing. But Sean Barry is one of the, well, 2 famous sort of chemical precursor developers, together with Anjana Devi from, she's now in at Leipzig Institute in Dresden. Okay, I want to thank you with these takeaways, and let's only go through the bold ones. So those deposition etching is two of a kind. Yeah, that's where the yin yang comes in. But that way, and only that way, because of the unique 3D diffusion, deposition, etching behavior of the chemistry for those most advanced transistor architectures, we're only possible because of these 2 techniques enabling the complementary FETs and the fork sheets and what have you. Yeah, those patents were written by Samsung and by Hitachi, and so long ago, when they understood what the potential of etching and deposition in atomic layer sequence could do. And we were, our hindies were sort of saved for 10 years because of this already. Extreme UV not coming up and delaying, and still the throughput of EUV is still something like 38 wafers per hour, and end users want 200, as they did with the immersion EUV and what have you. But there's a lot of things possible, especially if you think about this triple sort of thing: dep, etch, clean, and so forth. Also intermittent cleaning, important. And I think we have not heard the last word about plasma tomorrow. Kerstos will tell, I think, most of it on isotropic versus anisotropic etching, the tricks that you can play. And what is this? Oh, and of course this explosion comes up with all sorts of mixes, all hardware as well as software, important, because I didn't talk about machine learning, but it comes in, it will come in, and I did not talk that much about metrology, but with the single wafer concept, there's much more possible. Or what else did I forget? Oh, I forget so many things, but I will not forget this. Oh no, that's not here now. But Maxime asked, did you also include a slide on the ECS conference in August? It's on Hawaii, so if you don't want to be there, but every 4 years ECS has a meeting there because we attract much more Pacific Rim people. And we have every year, every October, we do have an ALD and ALE applications symposium there. Last year it was in Gothenburg, near, well, next door. And then there were 78 abstracts, 4 full days. If you would like, well, you can look it up in the internet. That is October, Hawaii, the Prime, Pacific Rim, and the E is interchemical or so. Conference, I think that's it. Oh, yeah, that's my last.